Hello student, in this lecture we will discuss about the dynamic programming, and with the help of dynamic programming we will solve matrician multiplication problem. So dynamic programming is a method that is used to solve the optimization problem. The optimization problems are those problems in which we have more than one valid solution, and based on some criteria we decide which solution is better than others. Okay, this dynamic programming approach works in a bottom up fashion. That means we start from the bottoms and solve the smallest size problem and store its solution so that it can be reused in order to find out solution of another subproblems. And similarly, after finding out solution of those subproblems, we again store them, and those solutions of subproblems are again reused for finding the solution of the whole problem. Now let's discuss difference between dynamic programming and divide and conquer approach. Divide and conquer approach works when subproblems are independent and we want to the same size of problems again and again. While dynamic programming, we solve the subproblems of the one size once and store its solutions so that it can be used later on. In dynamic programming, these subproblems are dependent on each other. That means solution of one problems affects the solution of another subproblems. That means there is a dependency between the subproblems. Okay. These are the steps of the dynamic programming which are used for finding the solution of the problems. So as per the first steps, we have to characterize the structure of an optimal solution. That means we have to decide the criteria on which basis we are deciding our solutions optimal, better one or worse one. That means we should have to clearly stipulate the optimal criteria. In the second step, we have to define our recursive solutions in terms of subproblems. Okay. Now third step, we compute the optimal solution in bottom up fashion. And fourth step, which in a optional steps, it's used to find out the structure of the optimal solution. Structure means optimal solution means path of the optimal solution. How did we constructed the optimal solution? Now let's discuss our first problem, that is matrix chain multiplication. The matrix chain multiplication problem can be stated as follows. Let's say given a chain A1 to AN of n matrices, where for I is equal to 1 to n, matrix AI has dimension Pi minus 1 into Pi. Fully parenthesize the product A1 to AN in a way that minimizes the number of scalar multiplication. So this is the problem of parenthesization. This is not the actual multiplication of the matrices. We have to find out the way of parenthesization in such a way that we get the minimum number of scalar multiplication when we do actually multiply those matrices. Look at this. Matrix multiplication is associative, and also the parenthesization, that means different parenthesization would result same product. For example, let's say we have 4 matrices and the product of 4 matrices can be find out by using these 5 ways. Okay, so First of all, we can multiply A3 and A4, and when we get the product of A3 and A4, then it is multiplied with A2. Then whatever we get, it is multiplied with A1. Or we can multiply A2 and A3 first, then multiply it with A4. Then whatever we get, we multiplied it with A1. Okay. Or we can multiply A1 with A2 and A3 and A4 together, and after getting the solutions, or after getting the matrix multiplied by A1, A2 and A3, A4, then multiply them together. Similarly, these are two or more possibilities. So total we have 5 distinct ways through which we multiply these 4 matrices, and number of scalar multiplication varies in each case. So we have to find out which parenthization is best for us in terms of scalar multiplication. We want to minimize those scalar multiplications. So that's why clearly it's an optimization problem. Now we'll discuss multiplication of two matrices. Let's say we have two matrices A and B. A has dimension P into Q, where B has dimension Q into R, and when we multiply these two matrices, we will get another matrix C, which has the dimension P into R. Okay. Now, there is a simple algorithm for multiplication of two matrices, and let's say name is matrix multiply. It takes two matrices A and B. First of all, it checks the compatibility of the multiplication of these two matrices. For the compatibility of multiplication, column of A must be equal to rows of B. If these are not equal, then it will show a compatible dimension error, otherwise it multiplies. So for the multiplication, there are 3 loops. First loop is for I is equal to 1 to row of A, that means number of rows are P, and for second loop J is equal to 1 to column B, and column B is R L, then 1 to R. Okay, 1 to R. And for third loop, K is equal to 1 to column of A. This is nothing but Q. That means this statement, in which finding out each element of C, will get executed P, Q, R times. So the time complexity of this matrix algorithm is PQR. Okay, so that means, or in this statement we are multiplying these two values. That means number of multiplications would be PQR. Okay, this is the number of scalar multiplication. Okay, so number of scalar multiplication is PQR. So we have to minimize these multiplication in our problem. So sometimes different parenthization yields a different scalar multiplication, and sometimes variation is very, very large. For example, let's say we have 3 matrices. Matrix A, matrix A has dimension 10 into 100, matrix B has dimension 100 into 5, matrix C has dimension 5 into 50, and there are 2 ways of the parenthization of these two matrices. First of all, we multiply A with B, and whatever we get multiply with C. Now if we multiply A and B, let's say we get a matrix D. Matrix D would have dimension of 10 into 5, and again we multiply it with C, then we get the final solution, and the final solution dimension would be 10 into 50. So number of multiplication in this case would be, when we multiply A with B, number of multiplication required 5000. Okay. And when we multiply with D with C, the number of scalar multiplication required 2500. So total number of multiplication, scalar multiplication required in this case is 7500. That means 7500. Okay. Now, if we multiply matrix B and C first, let's say we get matrix E, and the dimension of matrix E would be 100 into 50. Then multiply this E matrix with matrix A, then we get the final solution. In this case, number of multiplication would be, when we multiply B with C, would be 25,000, and when multiply with A with B, it would be 50,000. So number of total scalar multiplication is 75,000. As you can see, we have three size chain. That means we have to multiply three matrices, and total number of possible ways are 2. And when we find out the different scalar multiplication, in one case we have only 7500, in other case we have 75,000. You can see that means small variation yields a very large number of multiplication. So that means in one case we have only 7500 multiplication, or in another case we have 70,000. That's why this is very important problem. We have to find out these parenthesization in such a way so that we can have minimum number of scalar multiplication. I hope the problem is understood to you. Now let's proceed. How do we do that? Okay, now if we count the number of parenthesization of matrices, let's say we have n matrices, sequence of n matrices, and these matrices are compatible for the multiplication. So if we find out how many possible ways to get the multiplication of these matrices, that would be this number Pn. Pn is equal to 1 if n is equal to 1, otherwise it is Pk into Pn minus k. So let's say what is k. Let's say we have A1, A2, A3, A4 up to An. So let's say we multiply A1, A2, A3 first, then A4 to An, and then multiply those two. In this case, value of k is 3. Okay, value of k is 3. Okay, now this is one situation. In another situations, value may be 2. That means after matrix 2, we multiply these two matrices and then multiply these two. So we have to vary k, and value of k varies from k is equal to 1 to n minus 1, and each and every case we have to find out the number of scalar multiplication. Okay, so in exhaustive search, total number of multiplication goes in exponential, and it number of scalar multiplication are 4 to the power n by n to the power 3 by 2. Now, fortunately, we have a better approach, that is dynamic programming. With the help of dynamic programming, we can find out the optimal solutions. Okay. Now, in order to apply dynamic programming, we have to follow the 4 steps of the dynamic programming. In the first step, we define the optimal structure of our solution. That means we have to characterize the solution or we have to characterize the optimal solution. So in our matrician multiplication, so our criteria for optimization is parenthesization. So we have to decide the structure of optimal parenthesization. So optimal substructure of this problem is as follows. Suppose that an optimal parenthization of matrices AI to AJ splits the product AK and AK plus 1. That means after the kth matrix splits happen and the whole chain is divided into two subchains. Okay, the size of one chain is K and a size of another chain is J minus K. Okay, then the parenthization of the prefix subchain AI to AK, that means when we solve the subchain AI to AK, then this should be the optimal parenthization for AI to AK. Okay, for example, let's say we have A3 to A6. That means A3 to A6, we have to multiply. Value of I is 3, value of J is 6, and let's K is 5. That means the whole chain is divided into two portion, A3 to A5 and then A6. That means the whole problem is divided into two sub-problem. This is first sub-problem and this is second sub-problems. So in order to find out the optimal solution of this problem, we have to solve this sub-problem first and then this. And then after getting the solutions, we have to multiply these two. We have to find out the solution of whole problem. This is the optimal substructure. Okay, now come to the step number 2, recursive solution. In this step, we show that the solution of the problem is dependent on the sub-problem. That means if we want to solve the problem of bigger size, first of all we have to solve the solution. We have to solve the problem of smaller size. That means solution of the larger problem dependent on the solution of the smaller problem. Okay, let's consider Mij is the minimum number of scalar multiplication needed to compute the matrix Aij. Solve matrix AI to Aj. For the full problem, the cost of the cheapest way is to compute A1 to n. That means the whole size problem is n. Let's assume that optimal parenthization splits the product AI to AI plus 1 to Aj between AK and AK plus 1. Let's assume that optimal parenthization splits the product AI to Aj between AK and AK. That means splits happen after the kth matrix, and values of K varies from I to J. That means I is inclusive but J is not included. Then Mij is equal to the minimum cost of computing the subproducts AI to AK and AK plus 1 to J. So look at this equation. Mij, that means minimum number of scalar multiplication required from matrix I to matrix J, is equal to Mik, because splits happen after the kth matrix. So it is Mik, that means number of scalar multiplication required from matrix I to matrix K plus Mk plus 1 to J. That means number of multiplication required from K plus 1 matrix to matrix J plus Pi minus 1 into Pk to Pj. That means when we multiply these from I to K, we get one matrix A dash, and when we multiply again the second matrix, let's say we get another matrix B dash. Now in order to find out the solution, we have to multiply it again, and the scalar multiplication required for these matrices A dash and B dash are Pi minus 1 Pk into Pj. So with the help of this equation, we have to find out how many multiplication required for the how many scalar multiplication required for the matrix multiplication I to J. Unfortunately, we don't know the value of K. What is the value of K? So we have to vary this K. Okay. Now, this recursive equation assume that we know the value of K, which we do not. So there are only J minus 1 possible values of K, and which are K equal to I2, I plus 1 to J minus 1. Okay. Since the optimal parenthesis must use one of these values of k, we need only check them all to find the best. That means we have to check out each and every possibility. Thus, on recursive definition of the minimum cost of parenthesis gives the product A to J become this. Mij denotes the number of minimum scalar multiplication required are 0 if value I is equal to j. That means we have only single matrix, so there is no need of multiplication. That's why the Mij is 0. Otherwise it is equal to m minimum of Mik plus Mk plus 1j plus Pi minus 1 Pk into Pj, and value of k varies from I to j. That means we have to check out each and every possibility after varying the value of k and find out which has the minimum value, and this will happen for all values in which I is less than j. Now come to the third step. In third step we have to find out the solution of the problem in bottom-up fashion. So in this step we perform the third step of dynamic programming paradigm and compute the optimal cost by using the tabular bottom-up approach. The following pseudocode assume the matrix AI has dimension Pi minus 1. Pi, that means dimension of matrices are stored in an array, and if in order to find out the dimension of any matrix, AI matrix, that would be at two index, at index I minus 0 and ith index. So all matrices are put in the dimension of these matrices are put in an array. Okay, and the size of the array is n. The input sequence p0 to pn, where length of p is n plus 1. That means 0 to n. That means if we have n matrices, the size of the sequence, the size of the dimension array would be n plus 1. The processor uses an auxiliary table m which has size n into n, that is n rows and a column, for storing the value of Mij, that means number of scalar multiplication required from matrix I to matrix J, and host an auxiliary table S which has size n into n. This is used to store the value of the split, the value of the k, and which can be further used to find out the path of the optimal solution. So let's discuss in a simple example. As we have to do in bottom-up fashion. First of all, we find out the solution of all small problems. Let's say the smallest problem is for size 1, for which that is value 0, and after that we have to find out the minimum number of scalar multiplication required for size 2. For size 2 matrix would be from matrix 1 to matrix 2, for matrix 2 to matrix 3, then 3 to 4, and then n minus 3 to n minus 2, n minus 2, n minus 1, n minus 1 to n. That means this is for size 2. After getting the solution of size 2 matrices, then we have to find out the solution for size 3 matrices. So size 3 matrices would be 1 to 3, or 2 to 4, or 3 to 5, or n minus 3 to n minus 1, and n minus 2 n. This is for size 3. Similarly, after getting the size 3 solutions, now we have to find out the larger size, and while getting the solution of the larger size, the solutions already achieved for a smaller size would be beneficial for us, and we will use them directly because we have already stored them. Okay, that would be clear in couple of minutes when we will do example for it. So let's discuss here. So in this case we have to solve the matrix multiplication for size 4. So for 1 to 4, and then 2 to 5, then 3 to 6, and then n to minus 3 to n. Again move forward in this way, and in the second last step we have to solve the problem for size n minus 1, for 1 to n minus 1, and then m to n minus 1, and the last we have to solve the whole problem from 1 to n. That means we have to do in bottom up fashion. First of all, we solve the smallest problem and then gradually increase our size, and eventually we get the solution of our original problem. So this is the simple algorithm that is used for matrix chain multiplication order. Okay, what it does, first off it find out the length of p, length of array p, which is length of p is nothing but the length of array of the dimensions of the matrices. So as we have already discussed, length of p is n plus 1. If we have n matrices, so length of p minus 1 to get the number of matrices. Now for I is equal to 1 to n, mi is equal to 0, this is the number of scalar multiplication required for single matrix, and it is equal to 0 because in a single matrix we don't need scalar multiplication. Okay, now after that, this for loop for line number 4 to 12 do the number of do the multiplication or do the actual work. Now for first of all, we have to keep the length of our chain is 2. That means we have to find out the solution of n2 as we did in last slide, like this. First of all, we have to solve m12, m2, 3, m3, 4, m3 minus 4, m3 and n minus 3, n minus 2, and so on. So when length is 2, it will find out the number of scalar multiplication, and after that, in next loop, when value of L becomes 3, it find out the solution of length 3 solutions, and by varying the values of k. Okay, and so on. In the end, it will solve the 1 to n and store these values of the intermediate solution is due to matrices, which is R or matrices, or we can say table, which are M and. Now let's do one example of matrix chain multiplication. Let's consider that we have 4 matrices A1, A2, A3 and 4, and the dimension of the dimension array contains 5 elements because we have 4 matrices, and here has 5, 4, 6, 2 and 7. Now if we find out the dimension of A3, that would be P2 into P3. So it would be 6 into 2. This is the dimension of A3. Okay. Now, so as we have already discussed, we will start our solution in bottom up fashion. So first of all, we find out the solutions for single matrix. In that, for m11 is 0, m22 0, m33 0, m44 0. After that, we have to find out m12 size 2 matrix, number of scalar multiplication required for size 2, and for this value of k varies from 1 to 1. So it is m11 plus m22 plus p0, p1, p2, and the number of multiplication would be 120. So there is no choice for size 2 matrix, so the solution would be 120. Similarly, solve m23, it would be 48, and m34, it would be 84. Okay, now come to the size 3. For size 3, the first would be m123. Now this time value of k varies, and first time it is k, and then second time is 2. When it is k, it would be m11 like this, and m23 like this, and number of scalar multipliers p0, p1, p3. Okay. Now when the value of the k becomes 2, it would be m12, m33, and p0, p2, p3. Now if we find out number of in two options which has the minimum value is 88, we have to store it. Okay, while finding the solution of m11, we have already did m23 already. What is the value of m23? Value of m23 is 48. Okay, and value of m12 is 128. Okay, the minimum is 88, so we have stored it 88 over here. M13, similarly we will store M24. Again value of k varies from 2 to 3, so when value of k is 2, it is M22, then M34, then this value. If it is 3, it is M23, M44, and now we have to find out the values of these, and we will get the minimum value 104. So we have to store the 104 over here. Okay, so every time we have to find out the possible values of k, and based on the possible values k, we get the different number of scalar multiplication, and among all those possibilities we have to find out the minimum one. Okay, now this time m14, in this case value of k varies from 1 to 3. So when k is 1, when k is 2, when k is 3, if k is 1, then this is the left part, and this is the right part, or we can say right subproblems, k plus 1 to n to m24, and then this multiplication. Similarly, if the values of k is 3, then it will be m13, and then m44, and this multiplication. And among all these possibilities, the minimum value is 158, so we have to store it. So number of scalar multiplication, as we know we have only 4 matrices, so number of minimum multiplication required for multiply these matrices are 158. Okay, now this is the third step. Now come to the fourth step, constructing an optimal solution. So as we already discussed our algorithm, let's see our algorithm once again, is maintain additional data structure S which note down the, or which store the value of k for that particular minimum number of scalar multiplication. That means that value k is stored. So let's say we have already stored our k values in this table, and this is recursive algorithms which find out the value stored different size of problems. For the initial call would be S. So let's say this is another example. Let's say in this case we have 6 matrices. So initial call is the matrix, also the table S here, initial index 1 and the final index 6. So S16 is the first call, as we have clearly mentioned here. Then for S16 the value is 3, so it will return 3. Okay, that means first split is after matrix 3, then the problem is divided into S1 3, and second problem is S4 6. Okay, one call is here, another call is here, and with the help of this we get this solution. That means this is the parenthization. How do we parenthesize our matrix so that we can get our minimum number of scalar multiplication? Okay, so complexity of this is n square. Okay, thank you.